Hello, so my name is John Bussey, and today I would like to present on characterization of Mount St. Helens ash for use as a lunar regolith simulant. I'm from Washington State University, studying material science and engineering. Before I get started, a big thank you to my mentor, Dr. John McCoy, and Dr. Mark Weber, Sam Karcher, Natalie Smith-Gray, and Dave Bullinger for all of their help on this project. So, a bit of background on my project. Why investigate Mount St. Helens ash? So there's a team here at my university who's studying methods on how to remove lunar regolith or moon dust. So I'm going to use moon dust and lunar regolith interchangeably in this presentation, but particularly lunar regolith, from spacesuits and equipment. So they're testing using cryogenic liquids to try to clean off the spacesuits. And this lunar dust is highly abrasive, toxic, fouling, and harmful for both human health and equipment on lunar missions. So it can cause a hay fever type symptoms, and that's been reported from astronauts from the Apollo missions, but it can also be very detrimental to mechanical systems. So it can get into seals and bearings and affect spacesuit materials and electronics. And it can just generally be a very negative very effect. And so being able to test systems going to the moon, if they're compatible with this lunar regolith, is absolutely essential. And this lunar regolith is not easy to obtain. It's right, it comes from the moon. There's very limited amounts on Earth. And so you need to come up with a simulant or something to act like lunar regolith. And there are currently a lack of lunar regolith simulants, and the ones that are there are very expensive. Only 2 are on the commercial market. NASA stopped producing theirs around 30 years ago. And all the processes to make simulants today, the rock actually comes from Greenland, and it's very expensive. So the lunar regolith formed by meteoritic impact. So when meteorites hit the moon, they create this intense heat and pressure situation and shot out all these very small particles of lunar regolith. That is very similar to how the Mount St. Helens ash was created, right? And there was a volcanic explosion here in the Cascade Range of Washington, where Mount St. Helens exploded in 1980, 40 years ago, and let off these very small particles. And so this Mount St. Helens ash has been heavily studied, but it's never been thought of as for a simulant. And so the Earth Science Department here at WSU took this Mount St. Helens ash and took it off the roofs after the explosion and stored it up, and we actually have a bunch here on campus. So what we're really looking at is, can this Mount St. Helens ash be used, and is it similar to lunar regolith? So that's what we hypothesized, that the characteristics may be the same. That was because both were formed in extreme environments, and they're both similarly fine and abrasive. And this is kind of an overview image of lunar regolith. So some of the characterizations methods we used are listed on this slide. There's way too many to go into depth on, but most of this was because optical microscopy, right? Just using like a regular optical microscope, like you probably use in a high school biology class, you can't get a very large depth of field. So these are the methods we use to try to understand the properties, the surfaces, and the interiors of these particles. And I'd be happy to talk about some of these very specific questions in the group breakout meetings of the Western Regional Honors Conference. But here are the methods we use. We worked on this for the last 8 months. Basically, it's using a whole suite of assessment to look at the Mount St. Helens ash. So the elemental composition, we'll make this pretty quick. The Mount St. Helens ash and the lunar soil, particularly the highlands, because that's where the Artemis missions are going, are fairly similar, but not exactly the same. So particularly, they both are fairly high in levels of iron and titanium, which importantly affect properties. In addition, they have similar ratios of calcium and magnesium to sodium and potassium, which are important when thinking about the properties of minerals and glass. That said, the highland soil is a bit more extreme on those levels, but again, they're more similar. And this data was taken using XRF, X-ray fluorescence, from the literature right after the ash was collected in Pullman, Washington, which is where WSU is located. And then we verified this with energy dispersive spectroscopy. So one of the important characteristics was the petrology. So what is the geology of the things we're looking at? So the Mount St. Helens ash is mostly glass, around 80%, compared to 25 to 50% in the lunar regolith. So that might seem less than ideal, but both of them have a substantial portion that's glass and a substantial portion, about 20% for Mount St. Helens ash and 50 to 75 for lunar regolith, are crystalline phases. So the glass both contain colored glasses, which is notable because those are found less often on Earth. In addition, they both contain these things called agglutinates and breccias, and those are important because they're kind of jumbled pieces together, which form less often on the Earth. but are important properties because they are more abrasive. And it's interesting that we're found with mountain Helens ash in the lunar regolith. That's an indicator that the mountain Helens ash might be a better simulant. The crystalline phases are mostly calcium and sodium feldspars or plagioclast feldspars. There's almost no potassium feldspar, which is important because those have different properties. The most of the rock that the regolith is from the moon is mostly anorthosite, very similar to the crystalline phases found in the mountain Helens ash. Both are very low in mafic minerals, such as olivine or basaltic minerals, basaltic rocks. And so petrology is generally fairly similar. So we verified this via X-ray diffraction, which was congruous with what we were expecting. Particle size distribution is another essential thing to take in consideration, because the size of the particles really affects how detrimental it is to mechanical systems. So really small particles are much more likely to get into seals and bearings and electronics and affect those than larger particles. And so the mountain Helens ash was shifted. It's a bit smaller than the ash. That's the blue line on this curve versus the other dotted lines. So it's generally a bit smaller, but they're similar. And the good news is that the mountain Helens ash is actually a bit smaller, about between 1 to 20 microns is the center of the distribution. And this is really important because those are the particles that are most likely to be disruptive. So it's almost an asset of the ash that there is a higher prevalence of this in the ash compared to with regolith. And generally, situations are fairly comparable. Another interesting thing we did was X-ray computed topography, where we will actually look at the inside of these particles. And so this is the case of an aggregated particle where large glass blocks were fused together. And that is some more things that have been reported on the moon. And it's just a very interesting thing to think about with how the volcano exploded and how those pieces were formed. In addition, work on agglutinated particles. These are very similar to the aggregated particles where things are fused together. But on this, there's a block, and there's very small and granular pieces fused at the outside. And this is really interesting because these are the glutinate particles, similar to the glutinate particles found in the lunar regolith, that in reality are actually not found on Earth very often. They're pretty rare. And so this was a very interesting finding to find these particles on the outside. In addition, we were able to see bubbles on the inside. So you can see bubbles like this one right here as it goes around, as well as these bubbles here. And these bubbles and vesicles are highly prevalent in both the ash as well as the lunar regolith. And that is important because they affect kind of mechanical properties, the angularity, or how stiff the sides are and how much they can cause problems, as well as indicates that similar formation. So volcanic explosion versus asteroid impact. So when we talk about possible crystal structures from X-ray computed tomography, we're also able to see these small crystal inclusions, potentially making the ash particles be microlithic, you could say. And this is able to also determine that they were most likely plagioclast feldspar, which is an interesting finding and a unique use of this X-ray computed tomography microscope in order to be able to see by changes in density what those crystal structures are. The another really important thing is the morphology. So what are the sizes and shapes of the particles like? And I'm going to say this term angularity, or how sharp are the particles, right? Because oftentimes things that have existed in the Earth a long time have been eroded and weathered down to have more rounded edges. But those pointy, sharp edges are what you're found on the moon because there's less of that erosive atmosphere. And it's important to try to replicate that. So you can see here, the one on the left is mountain Helens ash and the right is lunar regolith. These particles, these kind of angular glassy shards, look very similar and highly angular, an important similarity. You can also see here you have kind of these aggregated agglutinate particles where you have little knobs on the outside of a larger chunk. Again, these also seem quite congruent and similar. And then blocky particles. These ones are kind of mineral particles. They're less angular, but they're both similarly angular and much more angular than if they had been seen on the Earth for a long time. And finally, you have these glassy pieces where you can kind of see the small nodes stuck to the outside of the glassy particles. And that is again relevant because they're just showing similar formation and they're going to have similar characteristics when used in testing. Finally, some thermal analysis we conducted on a thermal analysis machine. And this indicated that there was around 1% of mass was lost when we're doing the thermal testing, indicating that about 1% of the mass is water. Interesting result. Just means that a furnace is going to be needed to help liberate some of that water before it is used. And so overall, the mountain intelligence ash can be used as a low to medium fidelity simulant. So it's not absolutely excellent. It's not the highest stuff that NASA is developing. But that said, it's cheap and can be developed in very large quantities. There are somewhere around 100 barrels of 80-gallon drums full of this stuff here at WSU. And so it has the ability to be used widely. And it'd be much better for mechanical testing than chemical testing. So what I mean by that is that it'd be much better used for looking at mechanical systems. So joints, bearings, landing systems. And that is important because those are the systems that you need the most amount of lunar regolith, and the systems that have the highest amount of interface with the lunar environment. So to support that, the particle size distribution is similar, with even a little bit skewed to the smaller particles, which is important. Those are the particles that most need to be understood from mechanical testing. Excuse me. So for the morphology of the shape, they appear to be very similar. Since the formation was similar, they would be similar shapes, similar angularity, and have potentially agglutinate phases, which are rare on Earth and also quite relevant. The mineralogy is similar, although in different proportions. The fact that they're both mostly plagioclase feldspar, similar glasses, agglutinates, and breccias is relevant, even though they're not the exact same proportions. And the elemental composition is similar. They're both kind of in that higher end of the bones reaction series. It's a geology thing to study, but they're not perfect. So relevant, but that would definitely be a place where mountain ash maybe has a bit of a shortfall. So the next steps, it's currently used by the Hyperborean team, which is a finalist at the NASA's Big Idea Challenge here at Washington State. In addition, both NASA and the company Blue Origin have expressed serious interest in acquiring this ash for their own mechanical testing. There's currently planned testing of landing systems that would use this, and both are working with the university to establish a collaboration to acquire some of that ash. In addition, there's plenty of future research possibilities, including testing different properties such as electrostatic properties, abrasiveness, or durability. In addition, the ash can be examined for fundamental or basic glass research, especially there's some strange colored glass phases that aren't fully understood. In addition, the agglutinate particles are not well understood in either the ash or the regolith, and more study could be done there. And it could also be quite relevant to perhaps complement the composition or make maybe a mixture of mountain ash or Pullman, or maybe from Yakima, which is about 100 miles close to the volcano. So as the cloud of ash traveled from the volcano, the particles would settle out at around the same size. So if you went close to the volcano, you get some of those larger particles to round out the particle size distribution. And then some lessons learned about difficulty working with fine particles. Again, this stuff is supposed to act in a very destructive manner, and we found that was certainly the case with our equipment. And it also just further reiterated the importance of inter and intra-university collaboration. So thank you so much for listening to my presentation. I'm very excited to talk about this at WRHC, and I look forward to meeting you all. Thank you so much. Have a great evening.